seeing or that you might be doing. So if we look at, this is the homework problem we're doing tonight. This is the 6-C3, a plastic box, 20.3. Ding. So we've got this plastic box of mass 1.1 kilograms sliding along a horizontal table. Now I'd just like to point out before we kind of really begin this problem that the box is sliding, but nothing is pulling it. Okay, so it was like pushed or it started moving a while ago, and now it is sliding on the table. Okay, so nothing's really pulling it, anything like that. Its initial speed's 3.9 meters per second, and the force of kinetic friction opposes the motion, causing it to stop after 3.1 seconds. What's the coefficient of kinetic friction between the block and the table? And we note here, best friend. So those are our kinematic equations all the way back from units 2, 3, 4, 5. So kind of our old stuff there. So what we know in this, if we just kind of draw ourselves a picture, is we know we have some block and it is moving initially to the right with a velocity of 3.9 meters per second. Now a kind of subtle thing here that a lot of people miss is if this block is moving to the right with a positive 3.9 meters per second, that means we've already declared the right is positive through that. So that means our left is actually negative. Sometime later, and we actually know that time here, at a time of 3.1 seconds later, the block stops. So we know our final velocity here is 0. Okay? We are looking for what is the coefficient of friction between the block and the floor, because this floor is a little bit frictiony. What is that coefficient of friction? And remember, that coefficient of friction, it is something entirely dependent on the two surfaces you have. So are you looking at, grass and plastic, or sandpaper and like felt? That will change depending on the surface, and you need both surfaces to see that change. So what we're going to do here, since this is a component of friction, because friction is fun, we need to start looking at forces. And if we need to start looking at forces, that means we're also going to be using the equation F, and remember this is the net force, it's the sum of all forces acting on the block in a given direction, equals MA. And while we have the mass of this block here, we know, as given in the problem, the mass is 1.1 kilograms. We don't have an acceleration, but we can get it. That's our best friend there. If we think back to acceleration, acceleration can be defined as a change in velocity of final minus initial divided by some amount of time. And if we look at our scenario here, we have a final, we have initial, we have a time. So we can get a acceleration fairly easily. We'll just take our final velocity when the block came to a stop of 0 meters per second minus the initial 3.9 meters per second divided by our time 3.1 meters per second, or 3.1 seconds. This will give us meters per second squared. So we bust out trusty calculadora. We know we're going to get a negative answer here, so that's negative 3.9 divided by 3.1, and we get an acceleration of negative 1.2, we'll say 6 if we round it up, meters per second squared. Okay, so what we can do with this is we can take this in our F equals ma equation, and we can say that F net equals the mass 1.1 times an acceleration negative 1.26. So that's kilograms, and that's meters per second squared. Now, what we really need to concern ourselves with, if that's the force in ma there, what forces are acting on this block? Now, if the block is just sliding by itself and it's only friction, so what we have here for the block in our free body diagram, this is our block here, if it's moving to the right, we have a frictional force acting to the left, because remember, we assigned that the block was going in the positive direction, that's where its velocity was, So it's friction's opposing that motion to the left. But we also have, and we have to remember this now, we also have a weight from the block pushing down on the table or the floor or the surface it's moving on. And we know that weight equals mg. Now since the block isn't falling through the floor, there has to be a force opposing this weight. And that force that's opposing the weight, that's our normal force here. And since we're not floating upwards either with the block is just there, that means this normal force has to be equal to the weight, or at least the magnitude of it. It's in an opposite direction, but the size of it is the same. So that normal is going to also equal mg. So in our x direction, the way the block is moving, for our F equals ma equation, we only have one force. It is the force of friction, F, and it is in the negative direction, so it's negative. And that has to equal the 1.1 times negative 1.26. So F, the only force here is friction, equals ma. That's still holding true. If we expand this a little bit, because remember, we're trying in this problem to solve for mu, the coefficient of friction. That means we need to expand friction itself. Remember, friction is fun, mu times n. So we're going to have mu, what we're looking for, times the normal equals, and let's just multiply those 1.1 and the negative 1.26 together. We get negative 1.3, and we'll round up 9 newtons. Okay. First thing I notice here, just math-wise, these negatives are going to wipe each other out. They're going to divide out there, so that's nice. But if I want to solve for mu, the coefficient of friction, I need to plug in this normal. And I know from our diagram that our normal is going to be equal to the weight, which is mg here. So I can actually say that mu times, and then our normal force, is the mass times gravity. So our mass is 1.1, and gravity on Earth is 9.8, and that equals 1.39. If I take 9.8 times 1.1, I get that our coefficient of friction times 10.78, and that's going to be in newtons because that's a mass times an acceleration, equals 1.39 newtons, because I'm still carrying these newtons all the way through. If I just divide 1.39 divided by 10.78, just do a little division here, those divide out, we end up finding that the coefficient of friction is 0.128, so we'll just say 0.13. Note the units are newtons over newtons, so they actually go away. So this is our answer here, and we don't have to worry about anything else. That's how we incorporate friction in a problem. It's the same thing we've always done. We're setting up an F equals ma. We are setting up a free body diagram. It's just we need to remember that if we have a frictional force, friction is fun, and this normal force must equal the weight. If we do that, we're fine. Also remember, the normal force is only equal to the weight when you're on a flat surface. If you're on an inclined plane, then your normal force is actually equal to mg times the cosine of the angle of your plane. So you want to be a little bit careful about that. With that though, this problem's over. Finn.